Our next speaker, Dr. Don Rosenberry, is a hydrologist with 40 years experience with the USGS in Denver, Colorado. He's now in an emeritus position there. One of Dr. Rosenberry's primary interests is water budget models. He has collaborated with many competing interests for water rights throughout the U.S. Don will describe the significance of monitoring various parameters, including groundwater recharge, to address some management questions related to allocation of water during various climatic and other conditions. The title of Don's talk today is Modeling and Monitoring for Deep Creek Watershed Lake Level Releases. Don, thank you.
Well, thank you, David. And I just know that some of you are wondering, what's a guy from Denver doing here? What do you know about Deep Creek Lake? And I have to admit, not much. I have thus far not seen it yet, but I plan to today before I head back to Pittsburgh. But I've addressed these kinds of problems quite a bit over the years in places from, working on lakes in Maine and New Hampshire to working in Puget Sound, from working in Florida to working in San Francisco. You've got some substantial problems here, but I got to say, you're way ahead of the game compared to most people. So many times I'll go to a lake and there's been a problem. The lake has been abused. So I would say for 100 years, and there's really not much they can do about it. But you're ahead of the curve, I think, based on most other places. And I commend you for that. I commend you for being proactive. And I'll give you my outsider's perspective on the situation that you're facing and what groundwater might do to help you out. So I get it. There's competing interests here. You would like to keep the water in the lake, so you've got water on which to recreate. And the people downstream, they like recreation too. And there are a lot of fun things to do on the Youghiogheny River, as long as there's enough water. I drove across the river this morning. Now, there's not a whole lot of recreation going on at the moment on the river. But in the summer, when you've got one of the releases going, the 630 cubic feet per second addition to the river makes a big difference. And so I get it. There's competing interests here. And I can relate. So I grew up on a lake, one of the biggest lakes in Minnesota, Leech Lake. My hometown was Walker. And it was a vacation paradise. I don't know how many resorts were on the lake, but it was quite a few. And it was just great, except that that lake flowed into the Mississippi River. And the lake was actually an Army Corps of Engineers reservoir. So, when things got bad downstream, they needed to let water out of the lake to help out. So there were competing interests there too. And I also, it didn't occur to me until later, every one of the universities I attended was somehow water related. So I remember ice skating on Lake Bemidji in my undergraduate years and, recreating and running along the trails of the Mississippi River when I was going to the University of Minnesota. Every one of my education opportunities, there was water involved. So I'm kind of a water nut. And I've spent, as David said, I spent 40 years with U.S. Geological Survey, and I'd still be working with them, but things changed. I was kind of made a manager more than a scientist, and I realized if I retired, I could get back to doing the science. And I've been having a great time in the last 2 years doing just that. But prior to that, I worked on lake-related issues all over the place for a lot of different reasons, related to nutrients, harmful algal blooms, water budgets, low water levels, all across the country, and luckily in a lot of really beautiful places. So what's so bad about low water level? Well, I've found some really useful, interesting resources on the internet. And this was a website, Chris Nichols' website, I really appreciated. I thought it was a neat perspective. But to me, what says it all is this. When the lake level goes down, if you happen to like say have this piece of property here and your boat is up on the boat lift and the lake level drops faster than you can get your boat off the boat lift, let's say you're gone for a couple of days or a week, it's going to be there until next spring. It's a problem when the lake level gets too low if you happen to live on the lake. Totally understand. And this affects a lot of people. This is right from one of your websites. When the lake level gets down to 2458, almost 10% of all the docks in the lake are out of the water. And if it goes out of the water early in the season relative to late in the season, why, it's a big problem. Half of the time that you want to spend on the lake, you can't get to it. And it just gets worse the later in the year. And I understand it has to be that way, but you'd rather be operating over here than operating over here. But it could be even worse. So as bad as it is here some years, others have it worse. So this was a project I was involved with some years ago in Michigan, near Kalamazoo, Michigan. And this is a guy looking at his dock and wondering what happened to my vacation paradise. Where did the lake go? And it was a concern for everybody on the lake. So this guy's dock was somewhere over here, just out of the picture, and the shoreline had retreated a half a mile from his shoreline. I mean, it was a major problem. This is the dock. After a year or two of no water, you can hardly see the dock for all the weeds. And well, if you want to have a dock, you have to keep moving it every year farther and farther from the shoreline. There's the raft that the kids used to play on. I mean, imagine this. It would be so much worse than what you experience in the fall. And so they thought, hey, we got to do something. So they did. They pooled their resources. They hired a contractor. They installed a well that would pump groundwater into the lake to bring the lake level back up. Pretty simple solution. And it is. You think, okay, the well's back here somewhere in the trees, and here's 2,500 gallons a minute coming into the lake, round the clock, day after day. There it is flowing out into the lake, and the lake level comes up, and everybody's happy. Except the lake level wasn't coming up nearly to the extent that had been predicted. I mean, this is not rocket science. It's not hard to calculate the rate at which the lake level should rise, but it wasn't. Something else was going on. So they asked USGS to look into it, and I got involved. And so we used the standard techniques that we use to measure exchange between groundwater and surface water, physical measurements, not just modeling, but actual physical measurements to determine what's going on. I thought, when I got there, I thought, well, where could the water be going? It's going into the groundwater system. As the lake level comes up, some of it's going to flow laterally into the sediments that had been unsaturated. That's what I thought. I thought, yeah, it's coming up, but it's going up slower because some of it's spreading laterally. But that's not what we found. We found that everywhere around the lake, groundwater was coming in. So that doesn't make any sense. That should have helped the problem. And yet the lake level still wasn't rising to the extent that had been predicted. Well, there was one small area around the shoreline of the lake where groundwater wasn't coming in. In fact, there was this one small area around the lake where it was going out of the lake, and it was right there. And it happened to be pretty close to the pumping well. So what happened was they didn't install the well screen deep enough. So as they're pumping water out of the ground, it's drawing down the head or the water pressure in the groundwater so that it's lower than the head in the lake, which induces water to flow from the lake into the groundwater. So it was a big circulation cell. They're pumping it out of the ground, and it's just flowing right back into the ground near the pumping well. That was the problem. Now, eventually this was resolved. Eventually the lake level came back up, mainly due to regular rainfall again. But it's too bad that they didn't consult somebody earlier in the process. And I commend you because you really are addressing issues with your lake early in the process. This lake is only 100 years old. So let's look at the rule band here. Let's look at your particular situation. And really what you're looking at is this part of the rule band right here. When you're allowing the lake level to go down during the course of the summer, you want to keep it between this level and this level. And this is a rate of about a foot per month. That's the decline, the lake level decline that you want to maintain during the summer. Well, you can see data here from 2021 to 2024, and they're all within the rule band, so things are good. This is a little disturbing though, 2024, that was a pretty dry year, and you're right at the bottom edge of where you'd like it to be. And it's low way early in the season compared to where it normally is. And what I noticed was the steepest slope here, right along here, that's the greatest lake level drop of the period of record going back to 2021. And I calculated, well, what was that decline per day? And that with that slope, your lake level is dropping 1.4 feet per month rather than 1 foot per month. So that's your problem. The lake level has dropped earlier than the rest of the decline and at a greater rate in 2024. And that's in response to dry conditions, less than normal precip. It also was in response to your normal wettest month of the year. You didn't really get much rain in 2024 during July. And so rather than the decline being pushed off a month, it started to happen early because you didn't get July as your wettest month of the year. And if you don't get the rain in July, that puts you in trouble early in the season. So how much can groundwater help with this issue? How much can groundwater offset those years when you don't get that July bump in rainfall? That's what I'm going to talk about in part. Well, a water budget can help you address that situation, and you're already doing that. You're ahead of the curve. You already have a water budget calculation system in process. You already have a model that makes use of a water budget so you can forecast your lake levels. So you're doing really well. You're doing the right thing. The fact that you're all here today having this meeting indicates that you're ahead of the game, and I commend you for that. And this is right from your website. I mean, this is so impressive. I work with lake associations all across the country, and I don't think I've seen a lake situation like this, where you have so much information, you have so many people invested in this lake and willing to spend time and financial resources to keep it this way. So well done already. So when I say water budget, this is what I'm talking about. It's a simple equation, and we'll walk through it here. Precipitation plus groundwater coming in to the lake, plus surface water coming in, plus overland flow coming in, minus evaporation, minus any places where groundwater might be leaving the lake, and minus surface water out of the lake, and that's your big number, equals change in your lake volume, which is equivalent to change in your lake level. So that's a water budget. It's a great way to assess your situation and find out what the relative magnitudes of water that are coming to and from your lake are. But why groundwater? Why am I here talking about groundwater? Well, that's what I know. But also it's one of four components: precipitation, groundwater in, surface water in, overland flow. And it's not the biggest. Precipitation is the biggest number coming in. But groundwater is the steady, reliable water source. When precipitation shuts down, and you never know when that might happen, groundwater is going to continue to provide water to your lake. It's going to continue to provide water to the tributaries that then flow into the lake. So it's your ace in the hole. It's the thing that just keeps coming, even if you're in a drought situation. So it's really good to know what that number might be. So how much? How much is actually coming in from groundwater? That's the big question. Well, you could find out. You could turn this equation around. You could rearrange it. What happened there? Did I go forward or back? You could rearrange it And you could solve for groundwater, which is this equation here. So I've got a large numbers here, groundwater in, and that's a net number because it also includes what groundwater might be coming out. I'm assuming that's a small number. It might even be zero. Based on the data that I've seen on the web, it looks to me like groundwater is coming in around most of the lake. Most of the well data that I looked at, the groundwater level was well above lake stage. But there may be some places where it's going out that we don't know about yet. But anyway, that's a net number. And then that's equal to the rest of your water budget term. So you can solve for that using the water budget if you have good data in the water budget. But you're never going to get it exactly right because every one of these measured terms has measurement error. And so you have to consider the error and the uncertainty in the water budget when you calculate anything by difference. And in this case, I'm talking about groundwater. So let's get a sense for what that measurement error might be because it varies based on the component. So precipitation, at any given spot where you're measuring precipitation, the precipitation gauge does a pretty good job. And I'm going to say you can measure precipitation to within about 5%. That's a pretty small error, but that's for one gauge. And if you assign the value measured at that one gauge to the entire watershed, it could be way off. I mean, you live here, you know that you could have a thunderstorm on one side of the watershed and it could be sunny on the other side. So you need more than one precipitation gauge, and I'll get to that in a moment. Groundwater, I say 25% here, but it could be 100%. Groundwater is hugely variable and it depends a lot on the ease with which groundwater can flow through the underlying sediments. And that depends a lot on the geology of those underlying sediments, which can include fractures and zones of higher permeability that we just don't know about. We know so little about what's going on down there. We've got several wells. We know what the geology looks like in some spots, but it's highly variable. And that's why groundwater, even when you measure it, the uncertainty is pretty substantial. Surface water. USGS does a pretty good job of measuring surface water flow, and they're good at picking places where you can minimize the measurement error. And the very best that they can do is about 5%. More often, it's more like 10%. Evaporation, when I started 40 years ago, that number evaporation here, I'm saying it's 15%. It was more like 30%. But we've gotten a lot better at quantifying evaporation. So I'm going to say, giving today's technology, we could probably get within 15%. Measuring the lake volume and converting that to lake stage, I'm going to say 10% error because where you measure it is not necessarily the level averaged over the whole lake unless you have 2 or 3 gauges, and few people have that. Averaged over time, that number is a lot smaller. But I'm going to say for any given water budget over a period of a day or a month or a week, I'm going to say it's close to about 10%. So sum together, that if you solve for groundwater by difference, you're going to be plus or minus 23%. So let's say 25%. So that gives you a sense for just how good you could be. But that is if you actually measure all of these terms. And I'm not sure, you must have some estimate of evaporation. I don't know what method's being used, but that might be improved upon. And I know you're not measuring all of the surface water that's coming into the lake. So that could be improved, and maybe with not too much additional cost. And I'll get to that in a moment. So let's look a little more closely at each of these terms. And we'll start with the surface water out because that is the big number. So you are really clever in the way you do this. So you know what's being diverted to the turbines when they produce power. And there's a pretty good estimate of what that number is. But what you don't know is how much is leaking from the lake. You know that there's something leaking here because there's a stream here that goes down into the Youghiogheny River, but it varies substantially over time. And that stream comes from the lake. Some of the water leaks through the dam. Some of it goes around the dam. There might even be some that's coming from around here, but we don't really know that. But what you do to account for all of this is you measure the difference in flow in the Yakagani River between the downstream site and the upstream site, which is a pretty good idea. I think that was a really good solution. And what happened to, there we go. So here's the equation, the surface water at the downstream site, or the total out is equal to the surface water at the downstream site plus the upstream site. Yeah, they're downstream plus minus upstream. That's how you get it, by difference. And this is what that looks like. So this is stream flow taken right from the USGS website. And this is 1 month during 2024 from July into August. And you can see it varies. You know, you get rainfall, it goes up, comes down, another rain, it spikes up. And that's the flow at Swallow Falls Park. And it averages about 20 cubic feet per second. And this is at the McHenry gauge, just downstream of where the turbines export the water to the river. And you can see these numbers here. This is when you've got a release going on. This is when about 620 cubic feet per second are flowing into the river so that people can have a fun ride on their raft. Or maybe they only open one of the turbines and then there's 315. That's this number here. That really dominates this plot. But when the releases are turned off, this is what the stream gauge looks like at the downstream site. And that value averages about 50. So 50 minus 20 is about 30 cubic feet per second is the amount that's being lost through and around the dam, in addition to all those controlled releases for recreation. But you're saying to yourself, so what's a CFS, a cubic foot per second? How can any of us relate to that? You know, it's a cubic foot and it's every second and there's 30 of them. It's hard to envision. So instead, what I like to do, and what I'm going to do today, is convert that number to feet, feet of change in the level of your lake. So 30 feet per second, 30 cubic feet per second equates to 0.016 feet of lake level drop per day. And you can convert that to a month if you'd like, just multiply that by 30, but that gives you a sense of what 30 CFS means to the lake level. So this plot is the difference between the flow upstream and the flow downstream in the Yakagani River. And here you can see that when the controlled releases are turned off, this higher value is about 30 and this lower value is about 15. So the amount that's coming out of the dam ranges between about 15 and 30 cubic feet per second, or between about 1/4 of a foot per month to 1/2 a foot per month. That's how much you're losing out the dam, in addition to the controlled releases. So that gives you a sense of scale of what's going out of the lake. But that is not everything. And actually, it's worse than really is happening, because you're not considering all the groundwater that's flowing into the Yakagani River between the upstream and the downstream end. All along this reach, it's almost certain that groundwater is flowing into the river. And so if you're going to determine what's going out of the lake based on the difference between those two gauges, you have to also consider how much is coming into the river between those two gauges. So that is an adjustment that you could make that would further refine what's going out of the lake. And I'll talk about that also in a little bit more, in a bit more detail. So I'm going to call this GW Yak in my equations that you'll see. And then let's look at what's coming in. So you have invested considerable resources. You're doing a great job. I can't believe although it's a fairly big lake, it's just one lake, and yet you've got 3 stream gauges on this lake already. In addition to the 2 that you have on the Yakagani to measure the outflow, you've got 3 measuring inflow. Yay, you. This is fantastic. You've got a lot of information that you can make good use of. So you've got a stream gauge at Cherry Creek, you've got a stream gauge at North Glade Run, and you've got a stream gauge at Arrowhead. 3 different places around the lake, giving you a lot of good information. And so I looked at these, I plotted, these are plots from, I think this is 2025 now. See if I can't see it, there's no way. Nope, 2024, July 2024. So the same as what I showed you earlier. So Cherry Creek averages about 0.04 feet per month. North Glade Run, 0.007 feet per month. Arrowhead Run, 0.003 feet per month. So that gives you a sense of what's coming in based on the 3 places where you're measuring stream flow. So initially, preliminarily, I actually calculated a little bit of a water budget here just to see what your data shows. So this, this orange line is the change in lake level per day. So it's all negative, which means that your lake level is dropping each day, but that's normal because we're looking at July. And maybe a little worse than normal because this was July of 2024, a particularly dry time for you. So that's the orange line. That's the lake level change. And the blue line is the water budget term other than the lake level change that we had readily available. So the stream flow in based on those 3 stream flow numbers and, the stream flow out and precipitation, but not evaporation. But you can see that that number is smaller, that meaning that based on the data that we had, there's an offset here. And we're missing about 0.01 feet per day because we're not accounting for all the water yet. But as a preliminary first cut effort, it's not bad. And it certainly follows the pattern. You can see the variability is pretty close. So you're getting there. But you already know a lot thanks to your investments. And we know based on just looking at this stream flow, this is the stream flow record at Cherry Creek, that, yeah, you get some rain and the stream flow goes up, and then it comes down, another rain, and goes up. But when it drops, it's a relatively gradual drop. And already that's telling you that there's quite a bit of groundwater coming into the Cherry Creek subwatershed. As compared to Arrowhead Run, you can see how flashy this is. When you get a rainfall, it goes way up and then it drops, it plummets. And within just a few days, you're right back to where you were again. There's very little groundwater coming in to the Arrowhead Run sub-watershed. And North Glade Run is somewhere in between. You've got some groundwater coming in, feeding that, in addition to the rain that comes on the watershed when it rains, but not as much as Cherry Creek. So you already know that. You know that groundwater is contributing quite a bit to the stream flow that's coming into the lake, and you get a relative sense of how much. Plus, you're measuring the flow out of Deep Creek Lake, so that's a good thing. And you already know the surface water out. So you're well ahead of the curve here. So how do we make it better? How do we get the water budget even more highly refined? Well, we know that the surface water out in July is about 0.044 feet per day during a dry time, that July of 2024. And when the turbines are turned off, it's about 0.016 feet per day. And I made an estimate of evaporation based on just assuming that it's about 5 millimeters per day. And that's based on my intuition. I've measured evaporation quite a bit in quite a few places. It varies in the summer between 0 and 7 or 8 millimeters per day. So I'm going to say 5 is a pretty close approximation, which equals 0.016 feet per day. Precip this year during this month was 0.012 feet per day. So a little more evaporation than precip, and that's normal during a dry period. Surface water in, measured by those 3 places, was 0.007, and I estimated groundwater in at 0.002 plus or minus 100%. So this gives you relative numbers, relative amounts for these terms. So here it is visually in font size. So surface water out is the big dog in the room. It's got the biggest font, and the next biggest is precip and evaporation, and then surface water in, and then groundwater in. So I suggest, to make things better, that you focus your resources based on the size of the numbers. So we could do better at estimating surface water out. That's your biggest number. And I'm going to show you some ways that you could also improve those other three numbers. So let's talk about surface water out. So I mentioned that you're missing the groundwater coming in between these two locations. So the surface water out number that you've got is actually bigger than it really is. You're not losing as much water as you think because you're not accounting for all the groundwater that's coming into the Yakagani between these two gauges. There's a pretty easy way to refine that estimate. You don't know if that groundwater number is 2 or 5 or 20%. It could range by quite a bit. Water isotopes, I would suggest, is a really good way for you to determine whether it's 2% or 20% or 1 or 30. It will give you a better idea of just how big that number is and how important it might be. And it won't vary that much over time, which is good news as well. It used to be that measuring water isotopes, and by the way, this isn't radioactive. These are non-radioactive. They're just oxygen 16, oxygen 18. They're just natural isotopes of water. And you can make use of that because the isotopic signature of water in a lake is different because when you have evaporation from the lake, the lighter isotopic fraction evaporates more than the heavier fraction. So the oxygen 16 evaporates away, leaving the lake heavier in an isotopic ratio. So that's got a different signature than groundwater or than the water in the river. And it used to be expensive to analyze. Now it's really inexpensive. I know people who have analyzers in their garage, and they have a little side hustle going on analyzing samples for water isotopes. It doesn't cost much money. I think this would be a great study that a graduate student could pursue. You only have to do it once or maybe twice. Do it sometime during the summer when things are dry. Do it collect the samples when you don't have any releases. So when the turbines aren't running. And it wouldn't be hard and it wouldn't cost much money. And it would give you an idea of whether you're looking at 1 or 2% or 20%. So that'd be one easy way to improve your estimation of what's leaving the lake. Precipitation, I mentioned 5% error. That's great, but that's only within close proximity of where you're measuring precip. By the way, I showed a slide and I forgot to mention it. Take a look at this. These are all the same time scale. And so you see 3 bumps on Cherry Creek. You got rain, the creek goes up, another rain, the creek goes up, another smaller one. Look at here, not very far away, North Glade Run, you got one big bump, and that second rainfall that fell over the Cherry Creek watershed didn't happen in North Glade Run. It's because it was a thunderstorm. That's just what happens in the summer. It's not uniformly distributed. And if you make one measurement of rainfall in one place and you apportion it to the whole watershed, you could be way off once in a while. So you can make better use of rainfall if you have more rain gauges. And I don't know how many you have in the watershed. I know you have at least 2. I know you've got one here for Cherry Creek and you've got one, I think, right here. But maybe you've got more. But if you had yet more yet, you could do an even better job. And if you have some from outside the watershed, you could make use of that data too. And you could weigh the value or the amount measured at each one of these gauges based on the distance that gauge is from your watershed. So if you could add another rain gauge or 2 so that you'd have a better idea of the areally averaged precip over your watershed, you'd get a much better number for one of the biggest numbers of your water budget. And it wouldn't have to cost much money at all. Rain gauges don't cost that much. So how about evaporation? Now, you have a water budget model, and the people in Pittsburgh that you've been working with, they must estimate evaporation some way. I don't know how they do it, but there's a good chance that it's based on air temperature. The simplest methods for estimating evaporation just use air temperature. There are 3 or 4 different approaches. But you could do a lot better with just 2 more measurements. If you had air temperature and if you had lake surface temperature, which you probably already have a pretty good handle on, and if you had relative humidity, those 3 things, if you were measuring those 3 things, you can get a lot better estimate of evaporation just based on those 3 numbers. You can do better yet if you add a few more variables, but the cost goes up a fair bit to do that. And I would say if you were to estimate evaporation just based on air temperature and humidity and surface water temperature, it would be a big improvement and it wouldn't cost much at all. So surface water input. I think there's some low-hanging fruit here that could help you improve your water budget. So you could add another gauge. You already have 3 and you're thinking, wow, we've already spent a lot of money. We have to spend some more. Maybe. It depends on how well you want to refine the water budget model. But if you did, you could add a gauge at Mountain Run, Meadow Mountain Run, and maybe Red Run, that's based on some data from Maryland DNR. But you wouldn't even have to do that. So you know what's going on in these 3 areas in blue, but there are all kinds of streams coming in. And if you could make measurements, just one-time measurements all at about the same time of what's coming in from all those streams relative to what's coming in where you actually are measuring the flow, you'd get a better sense for how well these 3 measured locations represent the whole watershed. And your Maryland DNR has already done this. That's the great news. You already know way more than this. I was astonished when I came across this study and I saw that you've got a great assessment of the surface water resources coming into your larger watershed. They've determined that there are 67 largely intermittent streams, 67 sub-watersheds within your larger Deep Creek Lake watershed. And of those 67 watersheds, you're measuring 3. Sounds not very good, right? However, these are 3 pretty big numbers. You can see these in the red boxes here. 20 of your streams contribute 75% of all the flow that's coming in. That's what the Maryland DNR has already determined. And 7 streams contribute half of all the water that's coming into the lake. So that's why I mentioned Meadow Mountain Run. That's a fairly big number. That's almost 7% of all the water coming in. You add that, if you were to put a gauge there, well, you've already gauged a big percent of what's coming in. But you wouldn't have to do that. You could make a simple assumption that you've already got about 25% of your watershed gauged. So I know this isn't great, but you could just multiply whatever you're measuring times 4. Let's just say that your 3 gauge measurements, those 3 places, that 25% of your watershed is representative of the spatial variability and the rest. So you just multiply by 4 and you'd have 100% of the watershed, right? Well, there's some uncertainty there, but let's give it a shot. So what I did was I multiplied your surface water inflow during that 1 month in July by 4 to account for the unmeasured part of your watershed. And I had just made the assumption that the groundwater that's coming into the Youghiogheny is about 5% of the difference that you have between the downstream and the upstream gauges. And I calculated a revised water budget, and you can see that the numbers are pretty close. The blue line is still lower than the orange line, which means that we're still not accounting for some of the inflow, but we're getting there. We're getting pretty close. The difference is about 0.002 feet per day, and we would attribute that to groundwater coming into your lake, directly to the lake. So that's a step forward. There's still a difference. You can still do better. And to do better, I suggest that you look into base flow. And I suspect that the consultant that you've been working with that has created the model that you already have has done just this already. but I just want you to understand this a little bit better. So base flow is a number that varies between 0 and 1, and it's an indication of the percent of flow in the stream that originates as groundwater that discharges to the stream somewhere along that stream reach. And so if you look at this, here's a stream flow record. So this is the stream flow in the stream. You must have had a rain event here because stream flow goes up, it reaches a peak, and it quickly drops down, and then it starts to drop more slowly over time. And so this first spike here is overland flow, direct runoff. And the second, this part of it where the drop is slower, it's less steep, is interflow. And I'll tell you what that is in a moment. But the base flow is the part that's contributed by groundwater. So it's this part of the hydrograph. That's the part that just keeps coming into the stream. That's what keeps the stream from going dry in between rain events. That's the number that would help if we knew that number for each watershed, because it varies for each sub-watershed. So here, this is direct runoff right here. So that's this part here. That's just what runs off the land surface during a rainfall. There can be a fair bit of it, but it's really short-lived. It just runs right off and then it stops. Interflow is some of that rain that infiltrates into the ground, but it doesn't reach the water table. It gets diverted laterally and it flows down the hill slightly beneath the land surface and ends up in the stream. That's this part. And then base flow is the groundwater, the saturated portion of the sediments beneath the land surface that's always flowing into the stream, that's coming in steady at a fairly constant rate all the time. That's base flow. That's the number that's keeping water in your stream in between the events, the rain events. By the way, when I talk about groundwater in, now instead of a stream, this is the lake shore. So the same things are going on all around the lake in addition to going on with your streams. So if this is the lake instead of a stream, you still have groundwater coming into the lake. So that GWI number in all of the equations that I showed you, that's this. This is groundwater flowing directly to the lake. That happens in addition to the groundwater that flows to the streams that then ends up in the lake. So I just wanted to make sure that that was clear. But back to base flow, if you have this a hydrograph like this, where the stream rises and then it drops more slowly, that's a larger base flow. And when it drops more rapidly, that's a smaller base flow. And I mentioned it's just the percent of the total stream flow that's derived from groundwater. And there are 6 or 7 different methods, empirical methods to determine base flow based on these stream hydrographs. And I suspect that the consultant you hired uses one of these, and it doesn't really matter which one they use. They're all somewhat arbitrary, but they all tell you the relative amount of groundwater that's coming into those streams. So that's really what you want to know, because you know what the real number is at 3 of your stream gauges. And you can take that real number and apportion it to the rest of the watershed if you know what the relative number is for the entire watershed. So I suggest that this could be a really good way to get a better number on surface water coming into the lake. And I'll just show you an example here. So here are your 15-minute stream flow data from one of the streams. And you can see, I think this is Cherry Creek. And you can see a lot of variability here. You can see it getting dry in the summer, wet in the winter, dry in the summer. This is multiple year record. But what's interesting is this number right here. This is the lowest number that you have during this entire period of record going back to, I think it's 2021. So what you can do is if you can find this number here, you would know what the steady number of base flow is during the driest time, during July and August of 2024, when things were at their direst. This is the number that's still coming in from groundwater. And that's the number that I think would really help you in determining the extent to which you can let water out of the dam and still have water under the dock. So it looks to me like October 7 and November 10, there wasn't any rainfall. And so the lake level is really, the stream flow is really low here. And so if it's really low in Cherry Creek, that's the subwatershed with the largest base flow number. It's got to be even smaller at all of your other streams that are coming in. And you can assume that since this is in October and November, evaporation is going to be really small. So you could just assume that's zero. And then you could calculate groundwater coming in as the residual of the water budget at that time. And that would give you a really good number for groundwater in. So I would suggest you do something like that. And you could even go back in the record farther. You could probably find other times when Cherry Creek is really low. And you could do that several times and get an estimate of the range of base flow during the worst times. And I've been talking to, is Morgan here? I thought that might be you, Morgan. Nice to meet you. We had some interesting conversations. Morgan's got a really good feel for what's going on in your watershed. You're lucky to have Morgan in your community. And one thing that he said early on during our discussion was, well, the model gives you a forecast of what the lake level should be doing. But during that 2024 year, the lake level, I forget, it either dropped more than the model predicted or less. But whatever that difference was, well, that indicates that the model is not quite right. You could tweak the model to make the model match the lake level change that you recorded. And so then going forward, your model is now refined. And the model won't get it right for all of the events going forward. So you can continue to iteratively tweak the model to make the model match what you measure. And if you do that, your model averaged over time is going to do a much better job of forecasting the lake level in the lake. So that's another method that you have at your disposal that wouldn't cost much. Well, it wouldn't cost anything, just somebody's time to tweak that model. And that's just probably just adjusting the watershed average base flow index. That's my guess. I don't actually know how the consultants did this, but it's a pretty good guess that that's what they do. You could just adjust that base flow number and you'd have a better idea. Your model would better match what you're seeing. One other thing to think about is we're assuming that groundwater flowing out is nothing, really small, not nothing, but really small. But maybe it's not. Maybe in some parts of your watershed, there's so much groundwater pumping that you might be inducing water to flow from the lake to the pumping well, kind of similar to what had happened at that lake near Kalamazoo. If that's happening, well, you need to know about that. So this is a plot I found on a USGS report that shows the groundwater withdrawals within your watershed over the years going back to I think that's 88. Maybe it's 92. What did I do here? Anyway, it is 88. Thanks. You can see it better than I can. So you can see the steady increase. Actually, it's increasing to a greater extent over time. And this was only 2007. That was 18 years ago. What is that amount now? Now you might look at that and say, oh, wow, that's 160,000 gallons a day back in 2017. It might be way more than that now. What's that? Sorry, 2007. Yeah, right. Yeah, 10 years earlier. But it's really not that bad because not all that water is lost. A lot of that water ends up going back into the lake. But if this water is removed and used to grow grass, quite a bit of that water is lost to the atmosphere. It evaporates. And if that's the case, well, that is a substantial loss of water from your watershed. And if that's happening, you probably should know about that. And I'm sure the data exists. This is just a report that I found online, but I bet your colleagues at DNR in Maryland will know what this number is. And if it's a situation like this, it would be good to know about it because you could regulate that. You could maybe reduce the number of newly permitted wells, for example. You probably can't do anything about the wells that are there already, but that would be good to know. And it's also will have something to do with the streams. So if you have pumping wells that are diverting groundwater that otherwise would reach the streams, that means that the stream water that's flowing into the lake is reduced as well. And if you have a situation like this where the pumping wells are pulling water out of the stream, well, that just makes the problem even worse. And this is nothing that would be new here. This is a problem that we have out west where I live. That's a big deal. You know, rivers or streams are going dry all the time, and even naturally that happens. But even out here in the humid east, it happens. These are a couple of pictures from the Ipswich River in Massachusetts, which normally looked like this in the fall and the late summer, and now looks like this because there's been too much groundwater pumping. And the groundwater level is drawn down lower than the stream bed, and the stream just loses water out the bottom and it goes dry. You don't want that to happen here, and it doesn't look like that's happening, but it's something to think about going forward. So that's all I have, and I hope I've saved time for questions because I'm sure you probably have some and maybe some ideas.
Coming up.
Thanks for the great presentation. Could you go back to the slide that showed Arrowhead Creek, where
Flashing?
you call it Flash?
Yep.
Because I want to tie that back to a conversation we had earlier about impervious surface. So can you explain to the audience about flashy and how it can be related to impervious surface as well?
Oh, yes, absolutely. Great question. So when you get rain, when rain falls on the landscape, there are three things that happen. It either hits the ground, maybe it's a sloping land surface, and it just runs down the surface and into the nearest low spot, which is typically a stream. Or that water can infiltrate through the surface and eventually reach the stream as interflow that I mentioned earlier, or it can go to the ground. It can go to the groundwater. And then it's in the groundwater system, and that'll eventually reach the stream or the lake. But if you have an impervious surface like a road or a parking lot or a sidewalk or a roof, that water isn't going to infiltrate the land. It's more likely going to run off. The roof will flow into a gutter, and the gutter will flow into a drain, and the drain will flow into the river. It'll run off the parking lot and go down some channel rapidly, and it'll end up in the river or the lake. It won't have long-term storage. And so if you have a stream that has a lot of development within the watershed, so that let's say there's a lot of parking lots, a lot of roads, a little town with streets and sidewalks and rooftops, it's going to look like this. You're going to get a rainfall, and you're going to see a big increase in rainfall in the stream, but then all the water that otherwise would have added more flow in the stream, like you see here, it's gone. It's just running off into the lake or into, some other drain nearby, and you don't have that gradual later discharge to the stream that you otherwise would have. It's already in the lake. There's no storage. There's no averaging of that rainfall input over days or weeks or months. It just comes in and goes out right away. Good question.
Another question here.
Appreciate your talk. Related to his question, I'm not disputing your interpretation, but these watersheds are very different sizes, right? So if we normalize to watershed area, maybe Arrowhead Run would not look quite as flashy.
So to normalize to watershed area, that really, I think it would still look flashy, but this spike looks really big here, but these scales are greatly different.
Yeah.
And so this spike is really a lot smaller than this one, because the biggest number here is I think that's 3. And this one is 6. So, it's already not normalized. Those scales are different.
I had a question about the groundwater outflow of the lake,
Yep.
your water budget. If you could go back to one of those figures that showed how you're using the upstream and downstream gauge.
Oh, sure. And by the way, that's the surface water outflow.
Surface water outflow, sorry.
Yep.
So am I interpreting this correctly that you're assuming the only water entering between these two gauges is from groundwater, but there's a decent sized tributary on the other side of the Yakagani of surface water that also comes in between those two gauges?
that here?
That might bias
Is
the
that here?
budget. We can't see that.
Yeah, if there are tributaries coming in, that would be the same thing as this GWI. So if you've got tributaries coming in between the upstream and the downstream, not related to the one that's coming out of the lake, yeah, that's another offset. That's another bias. That's another number that should be measured. I guess I didn't notice that when I was looking on Google Earth, but
Muddy Creek probably has a similar watershed area to Cherry Creek, maybe not quite as big, but it's a decent sized tributary that comes in on River Left.
then you're absolutely right. Yeah, you need to account for that as well. So if you could come up with an estimate of the extent of water that comes in from that, that would further decrease the outflow that you're calculating based on the difference between the upstream and downstream gauges. You do the same thing as you would by estimating the water coming in from groundwater flowing into the river, into the Yak. Yeah, good idea. That I'm glad you know about that.
Any other questions? Yes, sir.
Well, I had one. So back to your water balance equation. I think you said, if you just go to that previous equation you had, so the dominant terms are the surface water inflow and the surface water outflow, correct?
No, the biggest terms are the surface water outflow and precip.
Precip onto the lake or precip onto the watershed?
Precip onto the lake.
Okay, precip onto the lake.
Yeah.
Okay, so
Yep.
precip onto the lake and surface water inflow are the big components
For the inflow terms.
for the
yeah.
inflow. What's the big
Yep.
outflows?
The big outflow is surface water out.
That's what I said. So the surface water outflow. So basically, and then you said, well, because these are the big terms, let's focus more on these bigger terms,
Yeah,
which kind of seems like that makes sense to do, except when you realize that you're going to use the equation, you're going to turn it around and you're going to calculate by difference, the difference between these two big numbers. So let's imagine one of the numbers, the inflow's 1,000 and the outflow you get 999. So you'd say, oh, well, the difference is only 1, except if you realize that the error on the big term is, let's say, 10%, and the error on the other term is 10%, you can get into a situation where there could be a positive inflow or a positive outflow, and you really can't tell the difference between the two. So
exactly
you
right.
could spend a lot of time and energy and money trying to hone these big inputs and outputs down so you really are trying to narrow that gap, but you just can't get there. It's impossible. So here's another suggestion. Why don't you propose to these folks that they look only at the data for the period of the year when those terms, those big terms that drive the water balance of the lake, are the smallest? So in other words, pick the driest time of the year. You had a thing up there, July of 2024. It would have been a great time, but I would have done it differently. During those times, you have almost nothing coming in the way of surface inflow. Some of those streams may have been completely dry. I don't know. You didn't have much going out, I'm assuming, by the surface water route. Maybe some, you think there's 15 to 30 CFS coming out in that stream, right? Through the tow drains or what have you. So now your big terms are something different. Your precipitation's gone. It's dry. You said July, there wasn't any rain. Skip that one. So now we're into a time when you've taken some of these big terms completely out of the equation and you can focus just on the things you want to know, which is really going to be the balance between evapotranspiration and groundwater. Those are the two terms you have left. So you could really ratchet down the errors by just focusing on certain times of the year when those big terms essentially can be neglected. I think
Thank
that's
you.
another
Thank you.
possibility.
Thank you. That's exactly what I was saying. That's why I did these calculations for July. That's why I did them for July of 2024. No, that was my point, and I evidently didn't make it. Yes, you want to do these calculations when the big numbers are small and when the sources of error are small. You know, you can have a really small percent error, but if it's a big number, it's still going to be a big error. So
That number you get is going to be representative. That number is only going to be representative of the specific hydroclimatological conditions that those measurements were made under. In
exactly.
other words, you might not be able to apply that over the entire water year, for example. You do that at your peril. You might get away with it. It might make sense, but it might not.
Yes. Oh my gosh. I'm so glad that you asked that question. That is really important. And that's why you calibrate the model to those dry times when you can minimize the error of those big terms, but it's still not going to be perfect. These relative proportions of input terms are going to vary seasonally, and the model's going to not get it right during some of the time. But if the model gets it wrong when things are really wet, and you're worried about low levels in the lake, that really doesn't matter so much. You would like to have the model calibrated to those dry times. So that's why I did this during July of 2024, when the precip number was relatively small. When evaporation, although it was probably pretty big, it's still a smaller component of the total water budget. Yet, so that's a brilliant, I'm so glad you brought that up, because that exactly was my intent.
Yes, 1 second, I'll get over there.
Thank you very much. I think you did a great job with that. Maryland Geological Survey does have some local wells alongside the lake, and you're correct. Some of those wells are direct. What the lake level is what the well level is, but also they have some other ones that show that there's an increased groundwater level compared to the lake level. We do need to realize that we are in a fractured rock system, like you suggested, and sometimes those wells do not correlate at all with the lake, and sometimes they do. So depending upon where the fractures are and where the groundwater bedding planes and all the flow regimes are. We want to make a couple points. I think this is for the non-scientists in the room. I think your 23% is a plus or minus 23%, correct?
It is, yes.
Okay. So that's a total range of 46% potential error. So just so everybody's tracking that, that's plus or minus. The other thing, and I just want to make sure, because we have to watch what some of the intents of using this data are in the future. When we're talking about a quarter foot to a half a foot throughout a month, those projections, and you're trying to make it very, very well, I believe, and what reality is, because nobody can tell what the heck a hundredth of a foot is over time. But that's wonderful. But that is at full pool level, correct?
Yeah, no, I'm glad you bring that up too, because I used a constant lake area. And if you wanted to refine those numbers, you could, there are curves that you can plot based on the bathymetry of the lake.
Right.
So this could be refined far better than what I did. I just made a first approximation, used an assumption of a constant lake surface.
Right. So I think that's something we all need in this room need to be aware of. If you're talking about a lake drawdown that's already sitting at -6 feet or -8 feet, that surface area is drastically reduced. And that quarter to a half foot may result into something much larger because your divisor is smaller.
Absolutely right. See,
Thank
this
you
is
very
this
much.
is how far ahead of the curve you already are. You've got a lot of really well-informed people here that understand these processes. You need to take advantage of this local resource, and they're going to really help you refine the water budget model if you just ask.
Yeah, sure.
It does sound like we're entering the realm of zoning and permitting, so we suggesting that there'll be areas where we're now going to not have development? An additional ordinance for, this is a protected area for maintaining lake levels so that we're not pulling from groundwater. That's just a complication, but I. it's
Yeah,
okay.
no, I didn't mean to make any implications regarding management. I was just, with those last two slides, pointing out that you may have in some places a situation where there actually is more groundwater out than we think. And as far as how you regulate or manage that, that's a local decision.
Just for the audience who don't understand why we're talking about this so intensely, our foundation has been working on this water budget model pretty much since the first day that the foundation was founded. We are trying to come to some possible conclusions that such a water budget model could be useful in how much water is released from the dam in times when there is a drought. And that's not all the time. And thank the Lord, it's not most of the time, but about every 7 or 8 years, it seems to happen. And what you showed in some of your earlier slides about how many docks go out as that water level drops down is very significant for the lake as well as for those who play on the Yakagani. So we're trying to figure out some equitable way of management at that particular time. And we're getting closer, I think is what you're saying. But the foundation has spent a lot of donors' money on this. This, what we've done just now, is very, very helpful to that. And perhaps we'll have more questions during the panel discussion. In my estimation, this is what a true scientific symposium is about, is this back and forth presentation by the professor and then back and forth. And the Greek word symposium, you're supposed to be drinking while you're doing this. So we have coffee for everybody.
All right.
Okay, well, speaking of drinking, any other questions? We got a question in the back.
Thanks, Don. That was pretty cool. I like that. So I can't quite remember where, but I read a paper from a researcher in Texas, and they have some sort of sensor they can drag through the water, and they can see the relative contribution of groundwater. And I don't know whether they're looking at isotopes, but then when they matched up with the gauging stations, it helps them look at not just a grab sample at one place and another. It allows you to look at it over a whole, over the area that you're measuring. So I'll see if I can dig that up, but that's how they were looking at it.
There are quite a few of those studies around, and most likely that sensor was a temperature sensor. And it may have been a temperature and specific inductance sensor.
And that's what it was. It wasn't temperature. Okay. Yep.
Yeah. And so where groundwater in the summertime, usually groundwater is colder than the surface water of a lake or a stream. And so by dragging a sensor along a stream bed or a lake shore, you can do this also on a lake shore in the shallow margin of a lake. And that's where most of the groundwater is coming into a lake, is right near the shoreline. If there are places where groundwater is coming in particularly fast, the lake bed or the stream bed will be colder than upstream or downstream. And you can detect that pretty well with temperature. If the groundwater, the concentration of solutes in groundwater is different than the surface water, so that the conductance, or as was mentioned earlier, the ability for electricity to flow through water, that's just an indication of the number of total dissolved solids in the water. If it's greater in groundwater than in the surface water, then there's also a spike there. And those sensors can measure that really fast, just like temperature. So it's a good tool for identifying focused discharge of groundwater. And if, once you know that, you can quantify those rates, and that's maybe a substantial percentage of the groundwater that's coming into a part of a stream reach or a shoreline.
Got another question? Here you go, sir. Thank you.
Just a quick observation or explanation I'd like is how does erosion factor into this?
Well, erosion, I've been thinking about that. Typically, if you had uniform sediments along a shoreline with distance from shore, you would get greater amount of fine-grained sediment out in the middle part of the lake, and the sediment would be coarsest near the shoreline, because those fine-grained sediments can get suspended in the water column and they can move. So the silt and clay is going to be thicker farther from shore than at the shoreline. And erosion can further enhance that process. Any fines in the shoreline are going to get suspended in the water column and distributed over the lake. And what that does is it further concentrates groundwater discharge to right near the shoreline, in the closest 5 or 10 meters within the shoreline. That's where most of the groundwater discharge is going to occur. So I was thinking about that with regard to your thoughts about wake boats, that those bigger waves caused by those wake boats going at half throttle, making the great big waves, they're going to further enhance that process of winnowing out the fine-grained portion of the sediment and pushing it farther out from shore, making it easier for groundwater to flow in right at the shoreline.
Okay, any other questions? Well, my brain is hungry right now, especially after this one. Thank you very much. Okay, lunch is ready out in the outside. Yeah.